Hello, Mr. Eric. Hello, Mr. Ryan. How are you today?
Good.
Good. Okay, so today we talk about something very interesting, which is called derangement. Can you guess what this means? Derangement.
The opposite of range, I think.
Arrange, yeah? Arrange. What's arrangement?
Putting things in order.
Well done. Putting things in order. Derangement is not in order. Okay. So, but this is has a special meaning, which is look, if there are three numbers, yeah. What's arrangement in order? It will be 1, 2, 3, right? Yes. That's in order. That's because the first number is in the first place. The second number is in the second place. The third number is in the third place. Okay? Yes? So the derangement means that the one cannot be in its position. So it can be here or here. 2 cannot be in second place because it's not, I just want it to be in other places. And
3, 1, 2.
yeah, 1, 2. Okay, so that's the derangement. For example, like 3, 1, 2. This is one of the derangement sequence permutation. Yeah.
Yeah.
So how many? Look, just remind me how many total solutions if there are n numbers, and how many permutation? Remember we talked about this permutation. Yeah. What's permutation? 1, 2, 3. Is that if you're using 3 numbers, how many permutations you can get? Remember, how many possible numbers can the first number be?
3,
How many for the second number?
2,
How many for the third number?
1,
So what's the total?
6.
Yeah, 3 times 2 times 1. So that permutation for n numbers is n factorial. Am I right? Yes? Okay, so now, obviously, the total number of derangement is less than the n factorial, right? Because that's the total number of possible permutation, right? Which includes the derangement, right? Yes? Yeah? And so the question is, given the number n, everyone, we want to find out how many derangement permutation it can be. There are, okay? So for example, given number 1, okay, for example, given one number, how many different derangement sequence? It's just one number.
1.
No, 0, because look, 1 is in its place, so it can't be. It's not true. So it's there's none derangement. Okay. How about 2? 2 numbers. How many? 1, 2. How many? 1. Yeah, because it can only be 2, 1, right? It cannot be 1, 2. Okay, so look, so that's easy. Yeah, you got the concept. Let's say f is the function we are going to look at. F0, obviously there's no 0, so let's do f1 equals 0, right? f2 equals what? Right?
F2 equals 1.
Yeah, because they can only be 2, 1, right? 2 numbers you can only place in 2, 1. That meets the requirement, which is its number is not in its original position. Got it?
Yeah.
Okay, so now how can we calculate Fn? The question is how can we calculate Fn? Okay? Yeah? Okay, so now look. Alright, look, this is the interesting part. Yeah. Yeah, look, this is interesting, right? So there are n minus n numbers here. Yeah? Yeah? And I want to put the number n here. These are from number 1 to n minus 1, right? And I want to put number n here. Right? So I want to put the number n. So how I cannot put it here, right? Because this is not n will be original position will be here, right? Yes?
Yeah.
So how many positions I can put the n?
5.
There's no 5. I mean, how many positions?
6.
No, I'm not talking about the number. I'm talking about this is n.
N
n minus 1. Yes. So look, I put n. I can only put it in n minus 1 position. Yeah. Yes.
Yeah. Yeah.
Okay, good job. Okay, now, if I put it in this number k, for example, any number k, yeah? Yes?
Yeah.
And the k can be put here, right? Let's see, swap it, yeah? Yeah? Am I right?
Yeah.
Yeah? Because the n, this position belongs to n, right? Am I right? The last position belongs to n. If n is placed in the first n minus 1, so any number I swap it can be directly put in the last number, right? Yes?
Yeah.
Because this nk can just put it in the last position because this set is not does not belongs to this n minus 1, any of this n minus 1, right? Yes? So there are, if I put it here, if I k put it here, so how many numbers how many solutions are this kind of solutions? How many? So look, if I put an n here and I put a k here, so there are n minus 2 possibility, am I right? Yes?
Yeah.
Fn minus 2. Right?
Yeah.
Look, can you imagine? If I put a k at the last, eh? And put an n. So basically I pick one of the n minus 1 number. Yeah, the first n minus 1. And I swap it with n. Yeah, I swap it. So the rest will be n minus 2, right? Yeah? So I can just times it, n minus 2. Yeah, times it. Yeah? This is. And how about if I don't put a k in the last? If I don't put a k in the last, it means what? Sorry? If I don't put a number k in the last position, then how many positions can I put? How many positions can I put? Okay, so this will be, because this n plus 1, I need to put it outside, yeah? Because those together will be n minus 1. I choose n minus 1 possibilities. So that will be plus f what? Can you guess?
K.
No, there's no k, just n. N minus 1, if I put the number, if I want to put a number n in the first n minus 1, then the n minus 1, I pick a number k, and then k can be put at the last. K can be put at the last, and if k put it in the last, there will be fn minus 2 positions. Yeah? And then if I don't put it in the k minus, in the last position, that will be
Something minus 1.
n minus 1, right? Why is it n minus 1? Why is it n minus 1? So look, if I don't put it in, where are we? If I don't put the k here, so how many positions can we put? So it means there are n minus 1 numbers can permutate, right? Do you get it?
Yeah.
Do you get it?
Yeah.
Let's see if this is true. Okay, fn minus 1, fn minus 1. Okay, so this is a bit tricky to understand. So if I don't put the k in the last number. If I don't put the number k in the last number, so I have n minus 1. This is the solution of n minus 1, right? Yeah, it's the solution of n minus 1. Okay, so let's try. Let's see this. Let's see this if it works. Okay, so f3. Let's see, fn equals n minus 1 times fn minus 2 plus fn minus 1, right? Yeah? So let's see, f3 equals what? Equals 2 times 3 minus 1, 2. 2 times f1 plus f2. f1 is 0, f2 is 1. So that will be 1. So f3 will be 2. So Is it two way? 2, 1, no, 2, 3, 1, right? Okay, this is one solution. How about 3, 1, 2? Yeah? Alright? Okay, so that's the only two solutions. Yes? Can we look if I want to put so look, if I want to put the number n, the 3, so I can put it in, if I want to put the number 3, so I can put it here and put it here. That will be 2 position, yeah? 2. Everywhere, look, it will be 2. Right? When I put here, and then I can swap it with 2, number 2. So that will be F1, right? That will be F1 because there's only one. And then if I 3, if I put it in K, and K don't swap it with the last position. You see, don't swap it with the last position, then it will be F what? It will be only one possibility, right? If F3, this is the original place will be number 2. Number 2 is here. Number 2 is here. And then if I will put it here, and then 2 can go from. If you go from the last one, you'll be here, right? Right?
Yeah.
If you go from not the last one, it will be in the F, these two numbers. That will be 2, 1. Right? So that will be n minus 1. Right? It will be n minus 1. You see? N minus 1. Because look, if these 2 doesn't go into the last position, look, I pick a 3 here, right? 3, I want to put it 3. I choose any number of the first n. For example, I choose the number 2. Right? So if a 2 goes from the last one, right? Goes from the last one, then we don't have a solution because look, 3, 2, and then the first one is 1. So that will be, if it's swapped with the 2, then the solution will be F3 minus 2 will be F1, right? F1 will be 0, right? Yes? Look, you see? 3, I put a 3, I swap it with 2, right? Yeah? And 2 can go to the last, yeah? Swap it with 3, yeah? Yeah? If I swap with 2, then the solution will be F1, right? It will be only this one number. F1 is 0 because I can't put a 1 here in the first place, right? If it doesn't swap with the number 1, then it will be n minus 2 because there are n minus 2 numbers, or n minus 1 numbers for the n, right? Yeah? Got it? Look. Why this is n minus 1? I just, look, you understand this part, yeah? F n minus 2, yeah? Yeah? And what's this n minus 1? Look, if I pick the number 3, put it in here, and 2 doesn't go into the last, then they are n minus 1, right? Look, they are n minus 1, which is 2 numbers. Yeah? Am I? Got it? Yeah? Okay, so this is, what we call? This is, what do we call? Dynamic programming transition function. Got it? Or transition equation. What's transition? From a state to another state. Because I want to calculate Fn, then I can calculate F minus 1. Look, what's the difference between this and Fibonacci number? What's the difference? What's Fibonacci number? It's without this bit, yeah? Okay? Yeah. The difference between this equation and the Fibonacci number is this bit. Got it? Okay? So look, if we don't know this equation, if we want to compute, if we want to try to find out how many, what's your brute force search? Remember brute force? Try every possibilities, right? Yeah, and how many possibilities are there? Okay? And what? What's the complexity of the brute force if I want to try every possibilities and then check if each one is a derangement? How many possibilities if there are n elements? The permutation, total permutation. And
No.
3 numbers, how many permutations? What's the possibility of the first number? What's the possibility of second number?
6.
Yeah, so what's that?
3 times 2 times 1.
What's that? 3 what? What's
3 factorial.
Yeah. So how many n factorial? Yes. So n factorial for brute forcing all permutation, right?
Yeah.
And how to check if it one's permutation is different the arrangement or not? Oh, you need to go through this permutation once to see if the original value is in the original place, right? If it's in, then it's not a valid arrangement, am I right?
Yeah.
So what's the complexity of that? Go through once. What's that?
N.
Oh, n. Yes, well done. So the overall complexity is O n factorial times n. This is huge. This is too complex. It's not feasible. For n equals 10, that will be a lot. I mean, right? It's not feasible, alright?
Yeah.
So we can do this using dynamic programming. We just prove an equation, and we can just do this. And you tell me, okay? Fn column, yeah? If n equals 1, return what?
0.
Yeah. If n equals 2, return what?
1.
Yeah, this is quite similar than Fibonacci number, yeah? Return n minus 1, yeah? Times fn minus 1 plus f what?
X minus 2.
Well done. That's it. And what's missing here? It's not column, okay? What's missing?
A cache.
Cache. Because if you're not using the cache, what happened? The least intermediate numbers, like Fibonacci number, will be calculated over and over again. And the time complexity, because at each round, it spawns 2 paths, right? So the complexity will be O to the power n, right? This is still huge, right?
Yeah.
Yeah, so we want to add a cache. Or the notebook, yeah? Remember the notebook? Without this, with this, the compiler, the computer knows. If a computer calculates F10, for example, yeah? The next time you are asking for F10, you will return the value without calculating it, right? Yes? So without with the notebook, how do we do this? A notebook, yeah? And then you can just do this here, yeah? You can just add it. If n in notebook, yeah? Return what? Notebook n, right? And then before you return, you store this number in a value, alright?
Yeah.
In a value, and then you put it in a notebook, yeah? Okay? And then return what? Return what? I calculate the value, I put it in a notebook, I return what?
Notebook.
No,
Value.
value, yes. Okay, let's be
N.
with the minimization, okay? And how about we're doing this is called top-down dynamic programming. How about we're doing this bottom-up dynamic programming, okay? Alright, look. Let's be quick, okay? Look. F
Been
and
18 minutes.
yeah, that's okay. That's the same, yeah? Look, that's the same. Return 0 if n equals to return 1, okay? Otherwise, look, we have a value, dp value, array, remember? This is dp array, look. dp equals, let's say, 0 times n minus n plus 1, okay? Okay?
19 minutes.
Okay, look, array.
Mm.
And then I need to set the dp2 equals 1, okay? And then I can do this for I, let's say for I in range start from the number 3 to n plus 1, right? To n plus 1. Then I can do this. dp I equals I minus 1 times dp I minus 1 plus dp I minus 2, right? Yeah?
Mm.
This is basically we start from the dp, the number 2, and calculate number 3, number 4, number 5, until number n, yeah? And then return the last value, which is dp what? dp what? The last value of the array. Minus
1.
the last value always, okay? So look, what's the time complexity?
N.
On, yeah? Because each value we only calculate. What's the space complexity?
N.
On, right?
Yeah.
Because we're using array. Can we do it without a array? Like Fibonacci number, we are not using array, right? We can use the array, but we're not using array. Alright, look. We can, because look, every time we're calculating DPI, we only need, how many values do we need to calculate for, if we want to calculate the value I? How many values do we need to calculate?
I minus.
DPI minus 1 and DPI minus 2. So like two values, like Fibonacci number. You calculate the Fibonacci number, like the first two items is, for example, there are two Fibonacci number, 3 and 4. And what's the next value? What's the next value? What's the next value? Huh? What's the Fibonacci number if the first two items is 3 and 4?
The next two items.
Next one item.
7.
Yeah, you only need the 3 and 4. You don't need to take consideration of the previous, yeah, previous to 3, yeah, yeah. Okay, so for this is simple. Look, yeah. So let's say A B equals 0 1, right? Because we know the first item is 0, the second item is 1, and now we just need to do this. Look, I 3 to n and A B. What's A? What's the new A? What's the new A? It'll be the B, right? Yeah, exact Fibonacci number. And what's the new B? It'll be that equation, yeah? Which is I minus 1 times what? Times A plus B, yeah? Look, it's exactly the same except this. Yeah, it's like the Fibonacci number except I have I minus 1 here, right? Remember the equation? Yeah? And I can just return B, yeah? Got it?
Yeah.
What's the space complexity?
O-N.
No, I just removed the O-N. What's the space complexity?
O.
What's the what's the time complexity?
O-O.
Time complexity. What's the time complexity? How many iterations do I need to go here?
N.
N, O-N. What's the space complexity? This is a hard question. What was that before I using the DP array? That's O-N. And I remove it. What's the complexity? Time complexity? O1. Because there's no additional storage except those constant variables I need, right? I remove the storage, right? I don't remove the storage. So this is very highly efficient because it's very fast, yeah? It does not have a recursion. It does not use the... Remember when you use the cache, as long as you use the cache, the notebook, what's the space complexity? If you're using a notebook, what's the space? O-N, yeah, because then now we are not using any notebook thing, so the space complexity is O1, which is optimal, the constant, and the time complexity is just a loop for O-N. So that's the optimal solution, okay? Yes? Eric, any questions? Do you understand this problem? Derangement, yeah? Okay, let me give you an example. 3, 2, 1, 4. Is this a derangement?
Yeah.
What? Is it a derangement?
Yeah.
Why is it derangement? Why is it not?
In order.
How about 4? 4 is in the original place. Is it a?
Yeah. No.
It's not because 4 is in the original place. How about this?
2 is.
Yeah, 2 is. How about 3, 2, 4, 3, 2, 1?
Let's say it is. It is. Going backwards.
This is because none of them are in original order. How about 5 numbers like 5, 4, 3, 2, 1? Is it a derangement?
3 is.
3 is in, so it's not a derangement, okay? So, okay, for number 5 numbers, can you write the derangement? And that's it for today. Can you write a derangement sequence? 5 numbers.
2.
You can write 1 as well, right? You want to...
1.
5, 4. Yeah, well done, okay? Well done, that's very well done. Derangement, okay? What's 3, 4, 4, 3, yes? 5, yes? 1, 2. Well done. Okay, so you know pretty much this concept, okay? That's very good, okay? Okay, so you can say bye-bye to people.
Bye.
Bye-bye. See you later. Bye-bye.
Yeah.